Let's now consider the isothermal expansion of an ideal gas and also introduce the concept of a reversible process. First of all, let's talk about what the isothermal expansion or compression of an ideal gas would involve. Shown on this slide is the apparatus that one could use to do the isothermal expansion or compression of an ideal gas. And it's helpful to begin by thinking about what the word isothermal means. So once again, we can really learn a lot about words from knowing what the root words are that make it up. And the word iso stands for same, and then the word thermal is referring to temperature. And so the word isothermal means that the process occurs at constant T. Now, we've considered transformations of an ideal gas that have occurred at constant volume and at constant pressure. This is the first case where we're thinking about what would happen if you were to transform an ideal gas at constant temperature. This is what the apparatus could look like for doing an isothermal expansion or compression of an ideal gas. We have our gas, that's our system, located right here, and it is immersed inside of a heat reservoir, which helps to maintain constant temperature. This would be a really big heat bath that can be used to either absorb heat that's released by the system, or it could also be used to provide heat to get absorbed by the system in order to maintain a constant temperature. Now, to perform the expansion or compression, you have weight. And what you could do is by increasing the amount of weight that's being put down here, that will allow you to contract the gas by pulling in the piston and making the system occupy less space. And you can remove weight from this apparatus. And in removing the weight, that would allow the balance to move up. And that would allow the piston to move out. And that would allow the gas to expand. So that's how we would perform this expansion and compression. That's how we would be able to make adjustments of the volume. You're changing the weight that's being applied here. And in doing that, you're changing the pressure that's being applied to the gas. All right, now let's talk about what would happen if you were to do an isothermal expansion of 1 mole of an ideal gas at 122 Kelvin. This value of 122 Kelvin seemed kind of weird, but this temperature has been picked to give us numbers that are really nice to work with. Now, one way that we can represent this transformation is by drawing something called a pressure-volume diagram. This is basically just a graph that plots pressure along the y-axis and the volume of the system along the x-axis. And this will allow us to track what's going to happen as we adjust our system from an initial state of 10 atmospheres and 1 liter to some final state. So we're going to start at 10 atm and 1 liter, and that would be our initial point in the transformation. We want to expand the gas, and so to expand the gas, you have to decrease the external pressure that's being applied to the system. We'll go back to the slide here and look at the apparatus. If you remove some weight from here, that will mean that the pulley here moves up, and that will allow the gas to expand because you don't have as much weight pushing down on the gas anymore. What we're going to do is cut the pressure in half down to 5 atmospheres. And when we do that, we're going to draw an arrow straight down here because what's going to happen is we're going to perform this change in the pressure instantaneously. So the applied pressure drops instantaneously down to 5 atmospheres. And now that the pressure has been dropped to 5 atmospheres, that will allow the gas to expand in this first step of our expansion process. We know that pressure and volume are inversely proportional to one another. And so if you reduce the pressure by half, that should cause the volume to double. So you'll go from 1 liter to 2 liters. And we're going to represent that on the graph by then drawing a little arrow over here showing that we go to 2 liters. Now, one way that we can represent what's going on in this transformation is by now drawing a dotted line all the way down to the x-axis. And in doing that, we generate a rectangle. And you might be wondering, well, what's the point of drawing this rectangle? But when you consider what the area of this rectangle is, you get something very interesting. So the area of this rectangle can be found by multiplying the length by the width. Length of our rectangle would be the pressure. So that would be equal to the pressure times the width of the rectangle is the change in volume as you go from 1 liter to 2 liters. So when we see this formula, the area of this rectangle is pressure times volume. Think about what that would represent. We've seen an equation that looks like this, right? Pressure times volume tells you information about work. Now, work is negative pressure times volume, and this is positive pressure times volume. So the sign is different, but the magnitude would be the same. So the area of the rectangle represents the work done in this step of the expansion. That's one of the reasons why it's nice to draw these PV diagrams. It helps us to visualize the work that is done during the expansion process. We could calculate the work that's done in this step by saying work is equal to negative P times delta V. And the pressure here is at 5 atm. Right? And the change in volume is our final volume of 2 liters minus the initial volume of 1 liter. So the work for this first step, I'm going to call it W sub 1, is equal to negative 5 liters times atmospheres. Now, what we can do is perform the second step of this expansion. So to perform the second step of the expansion, we have to reduce the weight that is being applied to our system, reduce the pressure that's being applied to the system. And we're going to again cut it in half so that now the pressure is 2.5 atm. And when we do that, that's going to move us down right to here at a pressure of 2.5 atm. We know again that because pressure and volume are inversely proportional to one another, that if you cut the pressure in half once again, you will double the volume once again. So now out to a volume of 4 liters at the end of the second step. We'll then draw the line showing the transformation to our final volume of 4 liters, and then put in a dotted line bringing us down to the x-axis and making this rectangle. And again, the area of that rectangle represents the work that is done in this process. The work for the second step in the process is, again, negative P times delta V. Negative, the pressure for this step was 2.5 atmospheres, so 2.5 atm. And delta V is V final of 4 liters minus V initial of 2 liters. The work for the second step is also negative 5 L atm. Now, how could we calculate the total work for the process? That's found by adding the work for the two steps. So work 1 plus work 2, negative 5 L atm plus negative 5 L atm comes out to negative 10 L atm. And it's rare for us to represent energy in units of liters atmospheres, so we can convert this into joules if we want by saying that 101.3 joules is 1 LATM. And so we can say the total work for this process is negative 101.3 joules. Again, we can see and visualize the amount of work that's being done by the system simply by making this pressure volume diagram and determining the area of the rectangles that represent each and every step in the transformation here. Now, you don't have to do the transformation in just 2 steps. You don't have to just, do a very large and sudden change of the pressure to 5 atm and then another very sudden and large change in the pressure to 2.5 atm. You could do the process more slowly and in a greater number of steps. And we could do it, for instance, in a process of 6 steps. Let's take a look at what that would involve. This is the pressure volume diagram for the same transformation done in a series of 6 steps. And so this process is being done by making much smaller incremental changes to the applied pressure, right? We don't go and cut it all the way in half during the first step. You just make a small change here and a small expansion, and then another small change in the pressure and another small expansion, and so on, to go through all 6 steps to go from your initial pressure and volume of 10 atm and 1 liter to your final pressure and volume of 2.5 atm and 4 liters. Again, I'll remind you the area of these rectangles for each step, 1, 2, 3, 4, 5, 6, represents the work that's being done by these steps. And the total work would be the sum for each and every step. That would be the total work for the whole transformation. Now, I want you to compare this PV diagram for the 6-step transformation to the PV diagram that we looked at for the 2-step transformation. And I overlaid them both here. And I want you to tell me which of these two processes yields more work. So go ahead and look this over and then put in your answer. Having given you time to think about this, let's go over the answer. So what you can do is take a look at the areas of the rectangles that would represent the work that's being done in the different transformations. And for the 2-step process, you do a certain amount of work. The 6-step process involves the same amount of work that's being done for the 2-step process, plus this additional stuff that you have represented up here. So the 6-step process is yielding more work. So when you do the process slowly and more methodically, you're allowing the system to do more work. And this makes sense because the expansion steps are occurring at higher pressures when you are doing the process in 6 steps. When you do the process in 2 steps, you cut the pressure severely down by half. And so when the gas does the expansion work, it's doing that expansion work against a relatively low pressure compared to what you would have for the transformation that you do in a 6-step process. You don't make as severe of a decrease in the pressure, and so when the gas expands, it has to expand against a higher external pressure, meaning that the gas has to perform more work. Therefore, you'll get more work out of the system when you do it more slowly and methodically. Now, we can take this concept all the way out to its logical conclusion and think about what would happen if you were to do the process in an infinite number of steps. If you were to do the process in an infinite number of steps, then you should be able to get the maximum amount of work from the system, right? The more steps, the more work. So if we do the process in an infinite number of steps, meaning that we make infinitesimally small changes to the pressure and allow infinitesimally small increases in the volume all the way down from our initial state to our final state, what you end up getting is a curve that looks like this. Now, we refer to a process that's done in an infinite number of steps like this as being a reversible process. So let's talk about what that means, why we call it reversible. In a reversible process, you will have equilibrium between the system and the surroundings at every single point during the transformation because you're doing the process very smoothly and very slowly. And so that allows you to maintain equilibrium because you're making such small changes that the system's equilibrium is not disturbed. So we refer to this as an equilibrium transformation, or the word reversible is used in chemistry kind of synonymously with equilibrium. So you say that it's done at equilibrium, you can also say that it's done reversibly. So that's where that word comes from. And as mentioned before, when you do the process reversibly, you get the maximum amount of work from the system. Because again, the more steps that you do, the more work that you get from the system. So if you do the process in an infinite number of steps, you should get the maximum amount of work from the system. Now, to actually calculate this work, you would have to calculate what the area under this curve is. And to do that, you would have to perform some calculus. I'm not going to do calculus because I know that that's not a prerequisite for this class, and I know sometimes in the past when I've done it, people start to freak out, and I don't want people to freak out. So what I'm going to do is say, let's just pretend that we did some calculus to find what the area under the curve is. And when you do that, you're going to get the following equation. The equation that you get after performing calculus to find the area under the curve is this. And this is an equation that you're going to have to use. It says that the reversible work, or the work for this reversible process, is equal to negative nRT times the natural log of V final over V initial. We can use this equation to calculate what the work was for this reversible process. So for the reversible transformation, the work would be calculated by saying work reversible is equal to, well, again, just write the equation out, negative nRT ln of V final over V initial. And we did this transformation from an initial volume of 1 liter to a final volume of 4 liters. We said that this was being done with 1 mole of ideal gas. And because we're trying to calculate work in units of joules, the R that we should use should be in units of joules. So that should be the 8.314 joules per mole per Kelvin. we defined that the temperature for this transformation was going to be 122 Kelvin that we saw at the very beginning of this presentation, and natural log of the final volume of 4 liters over the initial volume of 1 liter. The work done when the process is performed reversibly is negative 1406 joules. Now let's compare that to the work that we calculated when the process was done in 2 steps. When the process was done in 2 steps, this process is what we would say irreversible. And the reason why we say it is irreversible is because the system and the surroundings are not at equilibrium with each other at every single point during the transformation. Let's take a look back briefly at the PV diagram to see that. In the PV diagram that we looked at earlier, we made a very large change to the pressure. And in doing so, we put ourselves in a situation where the system and the surroundings are no longer at equilibrium anymore. Equilibrium is achieved when you are at a point on this graph that corresponds to something that you would get from the ideal gas law. And the ideal gas law would not hold true having a pressure of 5 atmospheres, a volume of 1 liter, a temperature of 122 Kelvin, and 1 mole of a gas. If you plugged all of those numbers into PV equals nRT, you would find that equation is not an equality. It doesn't work out. You're only in agreement with the ideal gas law on this point, and on this point in the transformation. So when you're in between these steps, you're out of equilibrium. You don't have a pressure and volume that match up with what the ideal gas law would require if you were to do the process isothermally at 122 Kelvin. However, when the process is done reversibly, you are following what the ideal gas law requires, and we can take a quick look at that. All right, when the process is done reversibly, you're following along this curve that corresponds to the inverse relationship between pressure and volume. This curve represents the equation that P is proportional to 1 over the volume, right? So you're following along that line, and so you're in agreement with the ideal gas law. You're at equilibrium at every single point along this transformation. But when the process is done irreversibly, you have large periods of time where you are not at equilibrium between the system and the surroundings, and so that's the reason why we call the process irreversible. Now, we calculated that for this irreversible process, so we could say W for the 2-step process was negative 1,013 joules. And what we see is exactly what was predicted earlier when we were just looking at the graphs and comparing the shapes of the graphs and the area of under the curves that we were looking at. We said that the more steps you do a process in, the more work you get from the system. And when you do it in 2 steps, the work done by the system is negative 1,013 joules. When you do the process in an infinite number of steps, the work done by the system is negative 1,406 joules. So you're able to get the system to do more work when the process is done reversibly. Now, would you ever be able to do a process like this reversibly? Would you ever be able to get 1,406 joules of work from the system? The answer to that question is unfortunately no, because in order to do this expansion reversibly, you have to do it in an infinite number of steps, and it would take an infinite number of time to do a process in an infinite number of steps. You would have to make such small changes to the weight that's applied that the process would literally take forever. And so it is for that reason that you cannot actually do this expansion process for real in a lab. So why would we care about this? Why would we look at this at all? The idea behind it is calculating the reversible work gives you a theoretical maximum amount of work that your system can do. This is similar to in Chem 1A when we talked about the theoretical yield for a chemical reaction. We're interested in calculating a theoretical yield for a reaction because we want to know how much of a product can you possibly make if the reaction is run under perfect conditions. And then you can calculate a percent yield based off of that and see how well you did at the reaction. Did your actual yield come in pretty close to the theoretical yield? Do you have a percent yield that's close to 100? Did it come in way short and you got way less than a 100% yield? That's the idea behind this. The reversible work is like the theoretical yield for the work. And the irreversible work would be like the actual yield. And you can compare the two and see how good you did, how close you got to the theoretical maximum. And that's why we're interested in knowing what the reversible work is. There are also a lot of other important things that we can learn from knowing what the reversible work is. And let's take a look at that on the next slide. So starting with our equation for reversible work, let's think about what delta E and Q would be for this process. So we're going to get some very useful information from doing these calculations. Now for an ideal gas, I'll remind you that you can always use the equation delta E equals NCV delta T, always for any transformation. Remember, this equation always holds true for any transformation because E is a state function, delta E is path independent. So it doesn't matter that this is not a constant volume path. Delta E is always equal to the constant volume heat, no matter what the pathway is. Now, since the process is isothermal, that means that delta T is equal to 0. And if delta T is equal to 0, you get delta E equals NCV times 0, and anything times 0 is 0. Delta E is 0 here. There is no change in the internal energy of the gas because the internal energy of the gas is a function of temperature only. Since temperature doesn't change, there's no change in the internal energy. Now let's consider Q. So for Q, we can use the first law of thermodynamics. We know what delta E is and we know what W is, so we can relate them using the first law. So we could say delta E is equal to Q for this reversible process plus the work for this reversible process. Now delta E is 0, so 0 equals Q rev plus W rev. And you can solve for Q by subtracting W rev from both sides. The heat and the work have to be equal and opposite to one another in this transformation, right? It has to be that way in order to get no change in the internal energy. So Q rev would be negative work reversible, which is negative nRT ln of V final over V initial. The two negative signs wipe one another out, giving you the following expression for Q reversible. Q reversible is positive nRT times the ln of V final over V initial. And this equation is going to be really helpful as we move forward and start talking about how this equation for Q rev can be used to help us calculate the change in entropy for the system. That brings us to the end of this section, and we're, in the next video, going to talk about how Q rev is related to the change in entropy and how we can learn information from that.